Hello, this is Tom Irvine, and I'm the instructor for this series of shock and vibration webinars. And I again thank Dr. Curtis Larson and the NASA Engineering and Safety Center, NESC, for making this series of webinars possible. And we're continuing on with our stress velocity webinar unit, and this is the second part. In this diagram here we have a cantilever beam, and it's subjected to base excitation. And we're going to do a continuous beam model. That is, we're going to essentially start with the governing partial differential equation of motion and solve that. And I've got papers on my blog that go through that derivation process. And in this case, our sample cantilever beam, now when I say cantilever, it's fixed on the left end and it's free on the right end. It's going to be made from aluminum. It'll be the length will be 9 inches, the width will be 1 inch, and the thickness will be 1/4 of an inch. And we're going to assume 5% damping for all modes. And one of the things we're going to do, I'm going to go to our vibration data GUI here, and let's go to, so this is up to 6.4 as I make this recording. We have a function here called import data to MATLAB, and I'm going to call up a time history that we're going to be using in the second part of the webinar here, and it's going to be a library function. So library is in this middle column here, and it's going to be called SRS 1000G acceleration time history. Well, that's what it is. And for internal MATLAB workspace purposes, it will be called SRS 1000G_accel with units time in seconds, and amplitude is acceleration in G. And this data file is actually included in the zip file. So now that's in our MATLAB workspace, as it can be seen here, and I'll show you a plot of this time history shortly. Okay, let's go to our next slide. So for our next slide here, we're going to do a beam bending analysis, and this will be a normal modes analysis. So I'm going to switch over to MATLAB, the GUI here, and show you how to do this. So let's go to Structural Dynamics, Begin Miscellaneous Analysis, and this will be beam bending. Okay, so our boundary conditions will be fixed free. By the way, this script calculates the bending natural frequency of a beam. So we have a fixed on the left, free on the right. That's, in other words, it's a cantilever beam. It will be English units and 9 inches long. Materials aluminum. We'll have a rectangular cross section, and our thickness is going to be 1/4 inch thickness. The width will be 1 inch width. And let's go ahead and calculate the natural frequencies. So we see the first 4 modes, the modal frequencies of the first 4 modes shown in this box here. So the first is about 98 Hertz, and then about 614, 1719, and 3368 Hertz. Here's a picture or image of the first mode. So this end here is fixed, and then the free end is vibrating. The maximum relative displacement will be at the free end. For the second mode here, there is an internal nodal point at which no translation occurs, but there is rotation allowed. So there's one interior nodal point for the second mode. For the third mode, there are 2 interior nodal points. And for the fourth mode, there are 3 interior nodal points. Now we can also go to our command window here and see the frequency results. So there are the first 4 natural frequencies. Then the participation factors are shown here in this column. Now participation factor is in some sense a measure of how easily excitable a given mode is. So let's just say we have a uniform white noise input. The first mode would be the leading mode in terms of the resulting acceleration, relative velocity, relative displacement, and all that at the free end. And then as we include higher modes in our analysis, there's going to be a diminishing returns as to how much response is added by including each additional mode. Because as we go up higher in mode number, the participation factor is ramping down. Then here's the effective modal mass values, and we like to include enough modes to have about 90% or so of the total mass. So if I take this number here and multiply, this is actually pounds force second square per inch. So if I multiply by 386, the equivalent modal mass in pounds mass, LBM, is about 0.2. That's by including 4 modes. Well, what is the actual mass of the beam? So we've got 9 inches long by 1 inch wide by 1/4 inch thick by 0.1 pounds mass per inch cubed. So the actual total mass is 0.225 LBM. By including 4 modes, we get 0.2023 LBM. So it looks like we have about 90% of the modal mass with 4 modes. So that's saying we're good to go with 4 modes. Okay, let's go back to slides here, and I've got a pathway to get to this GUI menu or function, whatever it's called. Just a reminder there. And we already took a look at the modal analysis for the first 4 modes. Okay, let's take a look at a shock response spectrum specification. And this is SRS Q is equal to 10. And we have 10 hertz, 1,000, and 10,000 hertz with corresponding peak accelerations, 10, 1,000, and 1,000 G. This ramp here has a 6 dB per octave slope, so it's a constant velocity ramp. And then I show the breakpoint. This is one way we could get the breakpoints into MATLAB. In fact, let's go ahead. I think we're going to do something with that here shortly. So I'm going to copy and paste this into the MATLAB command window. So now in our MATLAB command window in our workspace, we have this array. These are the specification points. We'll use those a bit later on. Now I've already synthesized a time history to satisfy this SRS, and we've covered SRS synthesis in a previous unit. So if you're motivated and you like to really dig into the details, you can go back and synthesize your own time history to satisfy that SRS. And here is what it is. It's called SRS 1000G underscore Excel.txt. And I have a note, import to MATLAB workspace. And actually we've already done it because I've now established that as a library function. So this is the time history that satisfies that SRS. And it's the same one as shown on this plot here. So if we actually take an SRS of our synthesized time history, so the title is Acceleration Shock Response Spectrum, Q is equal to 10. The y-axis is peak acceleration, G. The x-axis is natural frequency in hertz. So I'm not showing the nominal here, but the nominal spec does begin at 10 hertz, 10 Gs, and then goes up to 1,000 hertz, 1,000 Gs. So this would be that 6 dB per octave ramp. And then the plateau is at 1,000 Gs. So we're good to go with our that transient pulse. So let's go ahead and enter in our damping. So to enter in our damping, actually we go back to this GUI here, and we go to these are called dialogues. Sometimes I call these pages or whatever, or menus. These are really dialogues. Okay, I need to get my terminology correct. We're back to this GUI dialog. We're going to apply a base excitation. And in this case, we're going to have uniform Q is equal to 10 amplification factor for all modes. We could, if we so desired, have a different Q for each of the four modes. Or instead of applying the Q, we could apply a viscous damping ratio, which 5% damping, or 0.05 is a ratio, would be equivalent to Q is equal to 10. So let's go ahead and save those damping values. And if we go back to our command window, you can see, okay, here's our first four modes, our bending modes, corresponding Q values and corresponding damping ratios. So that's all well and good. So we're ready to move on. It's good to just sort of double check. Just sort of as an aside here, let's take a look at our transmissibility. And if we click on transmissibility, so let's see, let's go from 10 hertz to 1,000 hertz. And we're going to take our response location to be the free end of this beam. So at the free end, it's 9 inches. That's the length from the left boundary, which is the fixed boundary. So let's calculate our transmissibility functions here. So acceleration frequency response function for x is equal to 9 inches. So this is the absolute acceleration divided by the base acceleration. In other words, g out divided by g in versus frequency in hertz. And you can clearly see the fundamental mode there. At, let's see, what was that? It was about 98 hertz. And, you know, I put this up to 1,000. I should have gone up to 10,000. So that's pretty easy to redo. Let me just go ahead and do that. We were missing a couple of modes there. Okay, here's going out to 10,000 hertz in frequency. So first mode, second mode, third mode, and fourth mode. Now, a characteristic of each of these four modes is that they all have a Q value of 10, because that's what we specified. But if you try and pick off the peak transmissibility at resonance, none of those peaks, none of those modes has a peak at 10. This one here has its peak of about, I like to round off a bit, so I'm going to call it 16. This one's about 9. It's about 5. This is about 3.4. But what we could do is if we could do the half-power bandwidth method. And if we do the half-power bandwidth method, we would in fact get a Q is equal to 10 for each of those four spectral peaks. So the point is, this being a continuous system, and this is true for multi-degree of freedom systems as well, if we want the Q value, we cannot pick off the peak value at each of the four resonances. Rather, we have to use the half-power bandwidth method. And let me see what the slides have us do next. So, okay, that's just, if you're highly motivated, what you can do is save that acceleration FRF, and you can go into our the GUI dialog for doing the half-power bandwidth method. But I'm going to skip over that for now. Oh, and also before we move on, we have a couple other plots. We have a relative velocity frequency response function at the free end. So that's the relative velocity, inches per second, divided by base acceleration in g, and then versus frequency in hertz. So what you'll see for all of these plots is the fundamental mode, that first mode, is going to dominate the response. But these other higher modes can also contribute as well to the different sort of metrics. And here's the relative displacement. Now, by the time we get to our relative displacement frequency response function, the effect of these higher modes is really ramping down. So in many cases, for example, if we have a white noise input, the response is going to be dominated clearly by the fundamental mode and almost exclusively. So that's just a couple of different frequency response plots that we can take a look at. Okay, so the next thing we're going to do is apply an arbitrary pulse. So it's going to be that shock pulse we talked about earlier. So I'm going to click out of the transmissibility function. And let's see where we need to go back to. And these dialogues kind of get overlapping with one another. And I may have to go back. Let me just double check something here real quick. Let's see if we, okay, this is where we need to go back to. So I went down to the MATLAB icon in the system tray. So we've already saved our damping values. We took a look at transmissibility just for fun. Now let's go to our arbitrary pulse, which is going to be that shock pulse we talked about earlier. So we've got different choices on how many modes we can include, and I think I'm going to call up an Excel spreadsheet here, and you'll see why in a few minutes. So let's call in our input array, which is going to be that SRS 1000G underscore Excel. That's the acceleration time history synthesized to meet our SRS specification. And we'd already preloaded that into MATLAB because it's a library function. A response location, this will be at the free end, so it's going to be 9 inches. And we're going to calculate the response metrics. And I'm going to make a little table here because we're going to look at the effect of including varying numbers of modes. So let's just have n be our mode number, the number of modes included, I should say. And we're going to take a look at our pseudo velocity in inches per second. Now our pseudo velocity in inches per second is going to be at the free end. That's where the peak pseudo velocity is going to be. But our peak stress is going to be, our bending stress is going to be at the fixed end. And it's going to be the von Mises stress. So I'm just going to say Vm psi. And it looks like I need to tidy this up a bit, like let's see, format columns, do an auto fit there. Well, let's make the, okay, I'm just playing around just with some cosmetic things here. And it looks like I need to make a little correction there. Okay, let's take these two columns and we're going to do format auto column fit. And we'll make all these numbers so they're just in the center. Okay, so we have our pseudo velocity in inches per second and our von Mises stress in psi. So let's see what happens for this shock pulse. Bunch of plots go by. Well, the bending stress at the free end is 0, so not much use in taking a look at that plot. Here's our relative displacement at 9 inches, dominated by the fundamental mode. So we have relative displacement in inches versus time in seconds. Here's the relative velocity at 9 inches, still pretty much the fundamental mode response, but you can see the higher modes are somewhat active at the onset. You know, actually, I've misspoken, so let me go back and correct myself. We're only including one mode in the analysis, but what you see here is some of the base excitation energy is filtering through. So you need to watch me on that, and please keep me honest, okay? And here's our response acceleration. This is, again, it's a single mode response, but some of the high frequency energy is propagating through from the source, which is the base excitation. Now let's go to our command window. In our command window we have some statistics, and the way I do this, in the command window what you're going to see is I have 3 locations including our one of interest. So we've got the fixed end at 0, the middle point 4.5 inches, and the free end is 9. So we have our accelerations, our velocities, our relative displacements, our bending moments, and our bending stress. And by the way, the stress calculation is set up so that we actually calculate the bending moment and then the bending stress. And I was talking about von Mises stress earlier, but actually I was getting myself confused with plate. When we go to plate analysis, we do von Mises stress. This is actually going to be bending stress, so I'm just going to call it stress. So earlier today I was working on plate analysis. That's why I had von Mises stress in my mind. So if you're a fan of von Mises stress, that's coming, but it's actually going to be coming when we do the plate analysis. But what we want to record now is at the free end with one mode, we have 100.4 inches per second pseudo velocity or relative velocity. And our stress is going to be 8,891 psi. So that is the stress at the free end. So this is just for a single mode analysis. Now what we can do is go back and we can redo this analysis, and we can redo it 3 more times. Each time we're going to include a higher number of modes. So if I click on 2, that's going to do the first and second mode. So first and second mode, so let's see, I'm mainly interested in these numbers here. So our relative velocity goes up by about 16% as we include the first and second modes together. Our stress, however, goes up by a smaller percent, maybe about 8 or 9%. And if we include 3 modes, for 3 modes, what we find is that our velocity at the free end, it's hardly changing from the 2-mode case. And the bending stress, it's about the same as before. Actually went slightly down, so there could be something going on with phasing or something. Differing phase angles of the mode. So going to the 3rd mode, actually, by including all 3 modes, the stress goes down slightly. And if we include 4 modes, the relative displacement, the relative velocity, it's to the same number of significant digits. It's the same as if we only included 3 modes. And then our bending stress is so the bending stress is really remaining about constant. So this is just showing you what happens if we go through the various number of modes, including only 1 mode, including the first and second, first, second, and third, and all 4 modes. And let's see what we have on our slides. I need to stick pretty close to our slides on this one because we're going to be doing a lot of back and forth things. They're going to get a little crazy here. So this is just the statistics for the single mode case. So we've seen these statistics before. And this was the time history, acceleration response time history for including just the single mode. Here is the relative velocity time history. And these plots are all at the free end, by the way, including just 1 mode. The relative displacement at the free end, including just 1 mode. And then the the bending stress, including just 1 mode. So stress PSI versus time in seconds. And here is just some statistics showing the relative displacement. Now x equals L, that's the... I need to fix this slide. Okay, x is equal to 0 is the free end, and x is equal to L is the free end. Okay, back up. Let's back up. Let me try this one more time. This is the fixed end at x is equal to 0, and x is equal to L is the free end. Let me get this right. So I need to make a mental note to myself to upload these slides to the blog. So at x is equal to L, which is the free end, we have this is for 1 mode only. We get 0.16 inches. The relative velocity was 100.4 inches per second. The acceleration was 255 g. The bending mode at the fixed end was 92.6 force-pounds, and the bending stress at the fixed end was 8,891 psi. And just a note here, both the bending moment and stress are calculated from the second derivative of the mode shape. And I've got a paper on my blog that goes through that derivation and those formulas. So we calculate the bending moment from the second derivative of the mode shape, and then we can calculate the bending stress from the bending moment. So here's the stress-velocity relationship for our cantilever beam. And actually this relationship should hold for all beam boundary conditions. So we have the maximum bending stress here, and then it's equal to the modulus of elasticity, and C hat is the distance from the neutral axis to the outer fiber. Then this is the second derivative of the modal displacement. And I have max here. These are all going to be the maximum values. Now, the maximum pseudo-velocity and the maximum bending stress occur at two different locations, in fact opposite ends of the beam, for the cantilever beam. Then this equivalent formula here, we have the distance from the neutral axis to the outer fiber, C hat, square root elastic modulus, cross-sectional area, mass density divided by area moment of inertia, times the maximum modal velocity. So if we use this formula, the bending stress from velocity for one mode is 8857 psi. So let's go compare that here. I'm actually going to do that in a better table later on. And okay, we got something funny going on with the fonts. Let's see, the font should be 11. So I'm going to put I'll put SV, that's the stress velocity psi for just one mode. Put those together there. I mean put these in the same Excel spreadsheet. So we're pretty close. Our stress velocity value is within 1% of the stress value from just our pure analysis, going through the partial differential equations and doing the modal transient. Actually, the C column here, we should refer to this as the modal transient method. Whereas this is a simplified method here, just taking our pseudo velocity, which also came from the modal transient, but then instead of going through that process of taking the second derivative, we just directly multiplied this. Essentially, all these terms become a single coefficient times the peak modal velocity. Now, to extend this to a higher number of modes, it gets a little bit fuzzy, a little bit of hand waving when we try and think about how this relates to including additional modes. But we'll go ahead and do that anyways. And oh, but by the way, the pseudo velocity of 100 inches, 100.4 inches is 12 dB less than the material limit for aluminum, and for a bare aluminum. We'll talk about that in an upcoming slide. So another function we have, another GUI dialog, is the stress velocity dialog, and we can go to vibration data, structural dynamics, stress velocity relationship. So let's do that. So let's go to, oops, got all these figures called up. Maybe I think it's about time to do close out all the figures, close all. Okay, let's go to vibration data. We're going to go to structural dynamics, and then we're going to go to the stress velocity relationship for structural dynamics. And the first thing I do is see that we have a little bit of error message. And these things happen. So we attempted to reference the field of a non-structure array, which is edit stress. And I'm not sure why that happened. I may end up doing some in-class debugging here. But let's put in our 100.4 inches. This was our peak modal velocity for one mode from our modal transient analysis. Okay, never mind the little error glitch that happened. It was operator error, which is fumbling around. The software is actually good to go. So this is saying that we have, from our stress velocity relationship, based on 100.4 inches per second, the maximum stress comes out to be 10,220 psi. Now this is actually the case where we have, let's see, let me go to the slide here. Ah, okay, another operator error. I knew that number looked too high. We need to be a little bit more careful as we go through this, at least I do. I'm talking to myself here. This script calculates the maximum global stress in a structure undergoing free vibration or driven at resonance. So it's aluminum, it is beam bending. Here's where I made my error. We have a rectangular cross-section, not a solid circular one. And really, I don't mind making errors in front of you. I know it's embarrassing for me, but you know, you might make some of the same errors. Okay, 88512, 8851.2. Well, I already told you that that was going to be the case here. Okay, so what I showed you earlier was 8,857. So some numerical round off or something going on there we're not going to worry about. But in fact, just to be a little more circumspect here, I'm going to change that to 1. So this is if we take the formula. So in other words, I think I want to make this 8851. So this is just taking the formula. So we take our pseudo velocity, our relative velocity from our modal transient analysis. We multiply by this coefficient, and we get our maximum stress at the fixed boundary for our cantilever beam. And this is the case for just a single mode. Now I think what I've done is I've gone through in the slides here and shown a couple other things. Let's make it full screen there. Okay, in this case, I'm not going to go through and do this now, but this is just a summary. So this is going to be our bending stress. X is equal to 0, fixed end, by number of modes included, or number of included modes. And these velocities, you've seen these velocities before. And these are the velocity stress values for in PSI. So we have, if we include a single mode, it's 8,851 psi, and then you can see how we increase the velocity stress as we include a higher number of modes. But there is a diminishing returns effect that does occur with including a higher number of modes. And let's see what else. We also have our fourth column, which is our modal transient stress, PSI. Now, the modal transient PSI is, and you've seen these 4 numbers before as well. And I think to make this a little more sense, I should have switched out those 2 columns. But the modal transient comes about from our the response to the arbitrary pulse. That's in the MATLAB script. It's doing the full modal transient analysis. And it's picking out the relative velocities and then actually going through that calculation of the relative displacement, looking at the second derivative of the mode shape and calculating the bending moment and then the bending stress therefrom. So in some sense, this fourth column, which is the same as this column here, is the so-called exact values. Well, they're so-called exact values for that particular base input. And these velocity stress values here, these are just sort of the, once we know what the velocities are, actually from this column here, we don't need to take the second derivative. We don't need to calculate the bending moment. We just directly calculate the velocity stress from this column here using those coefficients, material and geometry coefficients that I showed you on a previous slide. So this is showing that actually as we include a higher number of modes, our quick method, our quick calculation method, actually is kind of over-predicting the stress, and that kind of comes about from the hand waving that occurs as we try to apply the previous equation, which is back on this slide, for a higher number of modes, because this is just really set up for just a single mode response. So maybe this is sort of an action item for myself, is to give a little more thought as to how we can make that more accurate for the case of including a higher number of modes. But really, this stress-velocity relationship is just kind of intended to give us a ballpark estimates anyways, and the idea being that if we do this ballpark stress-velocity calculation and the resulting stress is well within the yield stress, then we say that we're good to go, and we don't need to do any further analysis, because just to do the normal modes analysis, for example, if we were doing a finite element modeling, which we all are going to do later on. Today we're doing continuous model, but for a finite element model, for example, just to get the relative velocity at the free end, and that's actually can be done with a coarse mesh. But if we want to get the modal transient stress, then we have to use a finer mesh. So we might need two different models, or it might take longer CPU time or whatever to run the higher mesh model. Well, for a cantilever beam, that's all kind of trivial, but if you had a complex structure, then it would not be trivial. Okay, let's see what else we can do. We also can kind of go back and revisit our multi-degree of freedom, SRS, calculation method that we covered in a previous unit. So let's go ahead and find out where this is. And we've already called in our specs. So this is just taking our natural frequencies from our normal modes analysis, and not even doing modal transient, but just taking the SRS and picking off responses from the SRS from our handful of modal natural frequencies, and then calculating the equivalent pseudo velocities and accounting for the participation factors, and then calculating resulting pseudo velocities, and then on to stress that way. So this is the really quick and simple method. So let me go to vibration data, and I need to go to structural dynamics, and let's go to beam bending. And okay, actually, let's just sort of I'm doing some unnecessary backtracking. Let's go back to this window here, or this dialog here. So this was the dialog after we had done our normal modes analysis. We had entered in our Q value for uniform modes, and we've already looked at transmissibility, and we took a look at arbitrary pulse. So if we go back to here and do our multi-degree of freedom SRS analysis, and then we can put in our SRS spec. That's the breakpoints that we called in earlier, and actually these breakpoints are down here as well, just as a reminder. So we go back to here, and we can have an option for how many modes do we want to include. So if, for example, we include 2 modes here, so we're going to take the first 2 natural frequencies and pick off the corresponding acceleration in g from the SRS curve, and then converting that to equivalent pseudo velocity in inches per second. And if we do that, you can see we actually have 2 different methods. And okay, so we just see we see the participation factor shown there. Our mode shape is here, and the mode shapes are just shown in terms of the 3 coordinates: the fixed end, the midpoint, and the free end. Then the pseudo velocity of each of 3 locations: the fixed end, the mid location, and the free end. And we actually have 2 multi-degree of freedom SRS methods. We have the square root of the sum of the squares in inches per second, and the absolute sum method in inches per second. So here are the resulting pseudo velocities. So let's keep in mind this 110 inches per second. I'm actually going to summarize these in a table here shortly. Then the relative velocities. But the point is, knowing the pseudo velocity, we can go back and use our material and geometry coefficients and calculate the global maximum stress. So in other words, this method bypasses the modal transient altogether. So this is a real quick and simple method that is easy to perform to get a ballpark estimate. So rather than going through all the steps of showing you how to do all the different mode cases, you can figure out how to do that on your own. It's just a couple of mouse clicks. Let's go to a summary here. And for this summary, so this is going to be at the free end, x is equal to L. So we've got, this is from the multi-degree of freedom SRS analysis, where we've bypassed modal transit method altogether. So we have 2 modes included, then 3, then 4 included. And the modal transit, these are the values we've actually already seen. And then the third and fourth columns here is just from direct from the SRS. We have the square root of the sum of the squares, velocity in inches per second, and the absolute sum. The absolute sum, just as a reminder, assumes that all of the modes peak out at the same time in inches per second. And our modal transit velocities are falling in between these 2 multi-degree of freedom SRS parameters, but are closer to the SRSS methods. So that means we have good agreement there between those relative velocities, or we could call them pseudo-velocities. And that means we would be good to go for calculating stresses from the multi-degree of freedom SRS analysis. And you can kind of figure out how to do that on your own. Or you can just go back to vibration data, structural dynamics, and there's a stress-velocity relationship. So for example, let's say that you had bypassed the modal transient altogether, and you had found out that the SRSS method says that you could get, say, let's just go ahead and use 112 inches per second. 112 inches per second. Aluminum. Okay, we got to be careful, get the right cross section. It is rectangular. Beam bending. Okay, wave speed about 200,000 inches per second, and the maximum stress is about 9,873.8 psi. And if we go back and look at a previous slide, yeah, that's ballpark. That's a ballpark good number. So this is a roundabout way of saying, if you're in a hurry, you don't need to do the synthesizing the waveform. You don't need to go through and do the modal transit. You can just do this shortcut method, the multi-degree of freedom SRS method. Okay, we're going to shift gears a little bit. Here's sample material velocity limits. So we have material, different types of materials, elastic modulus, English units, yield stress, mass density. Then we've got rod, beam, and plate. And these are the velocity thresholds for these configurations, these geometric configurations, and then for these different materials. And the first time I saw this chart, and you can look at like Gaberson's papers. He has charts similar to this. I thought, wow, or tables, I should say. I thought, wow, someone sure went to a lot of effort to find out what the velocity thresholds are in these materials. I was very impressed. But then I thought to myself, hey, wait a minute. No one has actually done that. What they've done instead is they've looked at this yield stress, and then using the stress-velocity relationship, and of course using these material properties in conjunction with that, they've calculated or backed out what the corresponding velocity thresholds would be for yielding for these different materials in these different geometric configurations. So for a beam, for beam that's aluminum alloy, 6061T6, the velocity threshold for yielding is about 402 inches per second. So that's kind of interesting. And I think the example we just did for our cantilever beam, it was about 100 to 110 inches per second. So we were well within the yield limit for aluminum in a beam configuration. Then you can see these other materials as well. Structural steel for beam and then plate. Let's go to structural steel and plate. Structural steel being a ductile material has a lower yield velocity than does aluminum, which is more of a brittle material. So 113 inches per second. Now, if you think back to that Mill Standard 810E severity criteria for military equipment, that threshold was 100 inches per second. And I think that number was determined in part by a consideration of what the structural steel plate limit would be. I think there's a connection there. As I think about this whole topic, I'm still learning, and there's some things I'm still kind of agonizing over and thinking about, at night when I have insomnia. Is that there's issues about strain hardening, and I'm not sure we really fully understand this high frequency loading of materials as much as we should. And here's just a couple of quotes. I'll just read these to you, and you can kind of draw your own conclusions. A material can sometimes sustain an important dynamic load without damage, whereas the same load statically would lead to plastic deformation or to failure. Many materials subjected to short duration loads have ultimate strengths higher than those observed when they are static. And that's from C. Lalane, or Lalani, however he pronounces his name. Here's another quote. Ductile, lower yield strength materials are better able to withstand rapid dynamic loading than brittle, high strength materials. Interestingly, during repeated dynamic loadings, low yield strength ductile materials tend to increase their yield strength, whereas high yield strength brittle materials tend to fracture and shatter under rapid loading. That's from Huston and Joseph. So I think that's getting into some of the strain hardening type characteristics of these materials. Of course, when we're talking about shock loading, there's people that say, yeah, we need to be doing everything based on strain rather than stress, and there's some good arguments for that, but that's maybe in some future webinar. Just a couple of, I think we've kind of talked about some of these things already. Well, the pseudo velocity, which is Gaberson championed for many years, he and others think it should be the primary metric for our shock response spectrum specifications and testings. And of course, getting the mill standards to change. I mean, we're talking paradigm shift here. So this mill standard 810G says the maxi-max pseudo velocity at a particular single degree of freedom, undamped natural frequency, is thought to be more representative of the damage potential for shock, since it correlates with stress and strain in the elements of a single degree of freedom system. It is recommended that the maxi-max absolute acceleration SRS be the primary method of display for the shock, with the maxi-max pseudo-velocity SRS the secondary method of display, and useful in cases in which it is desirable to be able to correlate damage of simple systems with shock. So this is, the paradigm has not changed yet. We're still primarily using absolute acceleration as the primary metric for SRS, but there is some consideration being given to pseudo velocity, and personally, I like the one-size-fits-all method of the tripartite or four-coordinate plot method, because that maybe we should specify all our specifications in four-coordinate plot, because that that has something for everybody. Okay, just a couple of conclusions here. The global maximum stress can be calculated to first approximation with a coarse finite element model. We're going to do finite elements later on in an upcoming unit. Stress-velocity relationships is useful, but further development is needed, including case histories, application guidelines, etc., and even consideration for multiple modes. Dynamic stress is still best determined from dynamic strain. This is especially true if the response is multimodal and if the spatial distribution is needed. The velocity SRS, the pseudo-velocity SRS, has merits for calculating damage potential, and the tripartite SRS format is excellent because it shows all three amplitude metrics on one plot. Kind of talked about some of this already. The stress-velocity relationship, it only gives the global maximum stress. It cannot predict local stress at an arbitrary point. It does not immediately account for stress concentration factors. Further work is needed to develop plate formulas. It's great for simple structures like longitudinal rods and beam bending, but it may be difficult to apply for complex structures such as a a satellite payload with appendages and where there are multiple materials. We need to give some further thought about when we get to plates and shells and complex structures about von Mises stress versus maximum principal stress and other stress strain metrics. Okay, so of course you're welcome to send me email. If you have any questions, I've got several emails that I monitor several times a day, so don't worry if it's one email or the other. I'll get it regardless. And I hope you've enjoyed this webinar, and we'll hope to see you back soon. So thank you and goodbye.